Hello and good afternoon, and welcome to this webinar titled Permanent Magnets and Magnet Arrays in EMS for SolidWorks. My name is Arvind Krishnan and I will be your presenter today. On behalf of EMWorks, I thank you all for joining us today for this short webinar. Before I start, just a few bookkeeping items. The first thing that I would like to let you know is everybody who has registered for this webinar, we will share a link featuring today's recording. So you will be able to view this webinar at leisure in the future. And you are welcome to share this link with your colleagues and friends who may be interested. The next thing is it's a format of webinar where it's pretty much a one way. So if you would like to ask me any questions during my presentation, I strongly encourage you to use the chat window that is available in the GoToMeeting console, and please type in your questions there. And at the end of this webinar, I will browse through the questions and probably answer a few important ones. As always, you can type in your questions anytime during the presentation. You don't have to wait till the end of the webinar. With this, let us begin our presentation today. Let's take a look at the agenda that we have for this afternoon. I'm going to start with a very brief introduction to our product, which is called EMS. Next, I will jump to the topic in hand today. That's about permanent magnets. So we will see how permanent magnets are defined in EMS software. I will pay attention to the material library and the definition of permanent magnets, and finally to the direction of magnets. We will take a look at all of these using a couple of examples that I have for you. So I will be sharing my SolidWorks and EMS screen with you, and where you will be able to get an idea of how permanent magnet simulation is performed in EMS. Then I'll briefly also talk about the ability to do parametric simulations. Using one of the examples, we will actually take a look at it. Finally, after this demonstration of the software, we will return back to the presentation where I will present to you the various EMS product bundles that are available. And then we will take a look at some of the questions you might have, and I'll try my best to answer them. Let me start with the introduction to EMS. EMS is actually a finite element based simulation software. It's an electromagnetic simulation software that is completely embedded inside SolidWorks and Autodesk Inventor. For today's demonstration, we will use the EMS for SolidWorks product. EMS contains both electric as well as magnetic solvers, and it can cater to a wide variety of applications. Some of them I've actually noted down. Most of EMS customers do designs of actuators, solenoids, motors, magnet arrays, high voltage circuit breakers and devices, inductors, transformers, and some power electronic devices as well. These are some representative samples of our applications, and to see a wide range of applications, please visit our website www.emworks.com. Now we have many customers all over the world. A few of them I've mentioned here. So the point is EMS is a widely used software in the industry, especially in the world of SolidWorks as well as Autodesk Inventor. It's very popular and it's the preferred 3D finite element based electromagnetic simulation for SolidWorks as well as Autodesk Inventor users. Now let me turn my attention towards the topic for this afternoon, which is how does one solve simulation which includes permanent magnets in EMS. Now EMS has its own fully customizable material library. The material library contains a small sample of predefined permanent magnets, and they are actually categorized according to the type of permanent magnets. For example, alnico, ceramic, neodymium based magnet, and samarium cobalt. Since EMS material library is completely customizable, users can actually create their own magnets and use them for simulation. So this is really the first step involved in using permanent magnets in an EMS simulation. Is really you need to have the permanent magnet in your material library. The next thing that one needs to do, which actually is done using SolidWorks, is to create the direction of the magnet. And don't worry about it, I'll walk you through a demonstration where it will become very clear. Now, permanent magnets can be defined using both global as well as local coordinate systems in SolidWorks. Now, let me quickly return back to SolidWorks interface, where I'm going to show you a few examples as to how a simulation can be performed using permanent magnets. The first kind of simulation that I have for you is a simple permanent magnet that is enclosed in a steel which is of shape of a C, as you see in the left. Okay, we have a magnet and a steel casing, and we are going to see how we can do a simulation of permanent magnet to find the magnetic field in and around the geometry, and also to see what happens when I rotate the permanent magnet. How does my field vary at a particular point in this air gap as I rotate my magnet? So let me just go to SolidWorks, where we can have an understanding of how this model is set up. Let's take a look at how this model was created. It's a 3D geometry. As you see here, I'm rotating the model. What I have here is a permanent magnet whose magnetization direction is along the major length of the magnet. Next, we also have a steel which is in the form of a C-shaped. There is a little bit of air gap as you see here, and I have a line segment drawn using SolidWorks. The objective of this particular simulation is to find out what is the magnetic field, say, along this line when I have my permanent magnet at various angles of rotation. And the angle of rotation is simply defined by using a mate in SolidWorks, where I'm mating the two planes, and right now it's at a 45-degree angle. Okay, so EMS is a completely embedded simulation tool inside SolidWorks. It's a gold certified partner product of SolidWorks. So when you install EMS, it creates a EMS feature manager, as you see here. And this is the place where you are going to organize your simulations. The first step in doing any EM simulation is what we call as to create a study. So from the icons here, or by using a simple right click, I can actually access the study menu. Now EMS comes with several different study types. The study type that we will be using today is called magnetostatic. Now one will resort to this particular study type when you have permanent magnets or when you have electromagnets with DC current. There are also other analysis types that we will not go into in this particular webinar, but there are also other webinars available on our website which talks about several of these study types. One of the things that I would like to mention here is the ability to parameterize. What I mean by that is you can take any dimension in SolidWorks and you can use that as a parameter in EMS to study how the magnetic results will change with various values of the parameter. For example, in this particular model, we can choose the angle of rotation of the magnet as a parameter. Remember the 45 degrees angle that I showed you, which was a part of a mate? It was an angle mate that can be chosen as a parameter. Now, once you create a study, EMS actually creates a study tree as you see here. Now, in this study tree is where we would define the various materials. For example, for doing any electromagnetic simulation, we would require what we call as an air geometry. Now this captures the magnetic field in and around the physical solid components. For example, the steel as well as the magnet. The magnetic field not only resides within these two components, but also in the air geometry around it. And to be able to capture that, one needs to model the air geometry in SolidWorks. I've simply done that, and I've used the air as the material. And the steel is also defined using 1010 steel. Now let's come to the definition of the magnet. To define a magnet, you have to right click and say apply material. Now EMWorks material library is fully customizable. It has a few magnets that you see here. So you can select the magnet that you would like. We have neodymium based magnets, we have ceramic magnets, alnico, and so on, samarium cobalt. But the material library is fully customizable, which allows you to actually create your own material and use them for simulation. In this particular example, I'm using N42 as the material of my magnet. Now, once you define the material, you have to define its direction. Let me go ahead, zoom in to the magnet so it is very clear how direction is defined. To define a direction, I have to right click and say coercivity direction. Now I have several different options to define the direction of the magnet. I can use the SolidWorks global coordinate system, but in this particular example, I choose to use the local coordinate system and using a coordinate system that I created in SolidWorks on the magnet path. So as you see here, I've created a coordinate system where the X direction refers to the major length of this magnet, and this is the coordinate system that I'm going to use to define the direction of the magnet. So I can use Cartesian, cylindrical, or spherical. In this particular magnet, it's a simple Cartesian magnet where the north-south is aligned along the major length, and I choose along the x-axis of the local coordinate system to be the north-south direction. With this, we actually complete the definition of defining a magnet. So let me repeat. We have two things to define a magnet. You have to define the material from the EMS material library. And second, you have to define the direction for the magnet using any coordinate system created using SolidWorks. Now, this completes the definition of the problem. In addition to it, I've actually created a line segment, and I'm interested in finding the magnetic field along this line segment for this magnet. So I have run this simulation prior to our meeting here. So let's go ahead and take a look at some of the results. Now, as far as the results are concerned, I can actually study my magnetic flux density. If you see here, this is a vector plot of my magnetic flux density, which clearly tells us how the vectors, the magnetic flux, is distributed in the magnet, in the steel, as well as in the air region around it. And you can read off the maximum value in Teslas of the magnetic flux density. Now you can actually even define the magnetic flux density not as vectors but also as a fringe type of plot. So let me go ahead and define what is called as a section clipping to see inside your model. So I'm going to go and here it's very clear the magnetic flux density in my model. So I also have the air geometry, and I can decide to show the model edges. So now this is the plot of the magnetic flux density. And I take the front view and zoom in, and you can see regions of high flux and regions of low flux. Now we can have another variation of the problem whereby I can change the angle at which the magnet is aligned to say 0 degrees. And then I actually created another simulation where the magnet is at 0 degrees, and we can study the magnetic flux density as vectors. Now this is what I mean. The magnet is aligned along the y-axis of the assembly where the angle between the two planes is 0, and you can see how the magnetic flux lines are distributed as vectors. So the problem is interesting because now I can vary the angle of the magnet as a parameter, and I can study how it impacts the magnetic flux at a particular location. So let me go back to the SolidWorks model, and you can see that I have a line segment, and what I'm interested in is to compute the magnetic flux density at various locations along this line segment, and I want to compare and contrast both the studies. So I'm going to have, for example, create what is called as a 2D plot where I choose my line segment, basically the endpoints of my line segment, and I would like to get the magnetic flux density, and I want to compare that result with my previous study. And say OK. Now this gives me the value of my magnetic flux density between the two studies. So when I have a 0 degree, there is very little magnetic flux density here compared to when I have 45 degrees where I have a sizable amount of the magnetic flux density starting from this point all the way to this point. Now that we have created the magnetic flux density and two studies, let me show you the parametric option available in EMS. Now I can actually define any SolidWorks geometry dimension as a parameter. For example, here I have chosen to define the angle of rotation of the magnet as a parameter, and by default it was at 45 degrees. Once I create a parameter, I can then create what is known as a design scenario, where I can have several design scenarios. Now here in this simple example, I have three scenarios where I have 0 degrees, what we saw, the magnet aligned vertically along the y-axis, then it's at an angle of 22.5 degrees, and finally at an angle of 45 degrees. So I've done a simulation using three different scenarios. Now, what I can do is run the simulation and take a look at the results using all the three scenarios. So the first thing we can see is like what we have seen before. Here is a vector plot of my magnetic flux density. In scenario 1, 0 degrees. Now scenario 2, which is 22.5 degrees, and scenario 3, which is 45 degrees. On top of it, I can actually create a plot of magnetic flux density for my all the three scenarios. So here I have the three scenarios. So I have maximum magnetic flux density at the starting point of my line segment when I have 45 degrees as the angle. Then at 22.5 degrees, I have a magnetic flux density as shown here. And when I have 0 degrees, I have very little value for my magnetic flux density. So this point can serve as a sensor which can actually determine the angle of rotation of the magnet. So a new neat application would be to design sensors where we can see the rotation of the magnet. So that can actually serve as a way by which you can understand, and if this magnet is attached to a shaft that is rotating, you can actually make that as a position sensor to understand the angle. Okay. So this is one example where we have seen how to define a magnet, how to do a parametric simulation, and how to look at the results for various values of a parameter. Now let me go ahead and go to another example. In this case, we have a Hallbach array, which is actually a magnet array, and we will see how to define this magnet array in EMS and how to interpret and look at the magnetic flux density distribution in the model. Okay. As before, we can create a study which is magnetostatic study, and then we can define the materials for my various components. As I mentioned earlier, we would need an air geometry so that we capture the magnetic flux density in the air region around the magnets. And finally, these 5 magnets are given a material N42 from our material database. Next comes the definition of the direction. And as I mentioned to you earlier, you can right click and define the coercivity direction. Here, because my model is aligned along the SolidWorks X, Y, and Z axis, and there is no rotation of any of the magnets, I choose to use the global coordinate system. In the global coordinate system, I've used the Cartesian coordinate system along the x-axis, but in the opposite direction. That kind of is highlighted by this arrow. So let's just take a look at one more magnet here. Coercivity direction. I'm going to zoom back in. Now this is direction along the y-axis, as you see here, along the positive y-axis. So that's how you define the coercivity direction for these Hallbach magnets. Now once you have defined all the magnets, we are ready to run the simulation. After running the simulation, you can take a look at the results. Okay. Now, I want to let you know that this is a finite element based analysis. So there's something called the finite element mesh, which I didn't go over so far, but I just want to let you know that the process of solving involves first creating a finite element mesh. As you see here, it's automatically created by the EMS program. I can go ahead, hide my air geometry, so I can take a look at the finite element mesh created on the magnet, the cubical magnets. So now that we have the model setup and the solution, let's take a look at the results. So here I can take a look at the section plot of my magnetic flux density. So I'm going to go ahead and choose the front view, back view. So here you can see a section plot of my magnetic flux density. Okay. You can see regions where there is high value for my magnetic flux and regions where there are low. So this is a Hallbach array in which there is a decent amount of magnetic flux generated in the bottom below the magnet as compared to the top or above the magnet. So what we can do is we can use the probe command in EMS to actually highlight and give the values at various locations. Now similarly, I can use the probe command and take a look at those values on the top, and you can see that they are at least an order of magnitude smaller as compared to the ones in the bottom. And that can also be seen by the different blue regions. One is the dark blue, which is actually a much lower value compared to the light ones. And it's actually a good idea sometimes to view this plot in a logarithmic scale. So we have the ability to do that. So EMS, you can plot either in a linear scale or in a logarithmic scale. Now the logarithmic scale kind of exaggerates the distribution of the magnetic flux, and hence you can get a good idea of how strong relatively the magnetic flux is in the bottom half of the Hallbach array as compared to the top. And that's the expected behavior of such a Hallbach array. So far we have seen really how one can define magnets in SolidWorks and EMS, and you have also seen some simple magnetostatic simulations that we performed, and you saw what are the different types of results that one can extract using EMS. Now, I admit that this is not a comprehensive demonstration of step by step as to how this was done, and this is really not the venue for doing that. So if you are interested in how one can define these things step by step and you want to follow as a tutorial, we have several learning resources in the EMS program itself. When you go to help, there is something called the EMS demo viewer. Now the EMS demo viewer contains several examples that are preset and pre-run for you, and it also comes with a wide spectrum of tutorials. For example, there are a lot of tutorial examples here where we have this one. We also have the example of the Hallbach here, and for a lot of these examples you will also see a step-by-step tutorial if you find this little icon on the top. So should you ever decide to try out our EMWorks product, EMS for SolidWorks, I strongly encourage you to do that if you have an application related to magnetics. So you will be getting access to all these tutorial examples that come with videos, and that also comes with a little icon here that demonstrates how one can set up. It's a step-by-step tutorial. So there's also a getting started example and so on. So EMS really gives you the resources to actually learn the things that I showed you quickly. Also, I would like to send your attention towards a YouTube channel. So the YouTube channel, it's called EMWorks Inc. We have a YouTube channel which has over 100 videos available. So if you go to the playlist, they are also categorized based on, there are these start to finish videos which tell you how things are done in EMS. There are also all kinds of videos and tutorial videos that helps you to learn the program and also know more about it. Okay, so I strongly encourage you to use these resources. If you're already using EMWorks, please feel free to use these resources. But if you're new to EMWorks, you could also benefit by these videos to see our capabilities and see if there is a fit of our software for your application. With this, let me revert back to my presentation. And just a recap, we saw two examples, how we use permanent magnets in EMWorks. And we also saw how parameterization can be used powerfully so that you can do multiple scenarios where any SolidWorks dimension can serve as a parameter. And by all means, this is not a very exhaustive video showing you all the capabilities of EMWorks. For that, we have other resources which I shared with you just now, and I encourage you to look at them. Now, let me quickly go into the product bundles. How do we package and sell EMWorks? EMS. Now, EMS comes as two main packages. One is called EMS Electric, which really does electric problems. It has both 3D as well as 2D simulation capabilities. And EMS Magnetic, which does magnetic problems. Everything that we saw today is a part of EMS Magnetic. What I showed you is the 3D, but we also have 2D capabilities within the program. EMS Magnetic consists of three solvers: magnetostatic solver, which is exactly what we saw today. We also have AC magnetic as well as transient magnetic solvers. There are also several multiphysics options. Coupling to thermal, motion, structural, and circuit are the ones that we sell as add-on. We also combine these products and we have EMS Professional, where both EMS Electric and EMS Magnetic solvers come embedded. And also we have EMS Premium, which is everything that you can conceive to be using EMS for is available in EMS Premium. So this is how our products are bundled. For more information about these, I strongly encourage you to visit our website or contact our sales team. So their information is given here. With this, I would like to thank you all for patiently hearing to this short webinar that talked about how permanent magnets and magnet arrays can be simulated using EMS. As I mentioned earlier, a link to this recording will be shared with you, so you can go through everything that I did today at your leisure. You can contact our sales team, sales@emworks.com, for all information. Visit our website as well as our YouTube channel, which contains over 100 videos. So with this, I would like to thank you all for your time today. And right now, what I'm going to do is I'm going to take a look at some of the questions and see if I can answer them. So if there are any further questions, you can please write to us at sales@emworks.com, and then our technical team will be happy to answer you if you have any technical or sales related question. So with this, I would like to thank you all for attending today's webinar. On behalf of EMWorks, I wish you a very good afternoon and hope to see you later in a future webinar. Thank you very much and have a nice day.